A math teacher was arrested at John F. Kennedy Airport today when he was found to be carrying a compass, a ruler, and a calculator and a protractor. He is believed to be a member of the Algebra movement and has been charged with carrying weapons of math instruction. Anyways, we will be using algebraic properties today to do proofs. So more structured proofs where we go step by step. So using deductive reasoning, a lot of times we will be doing proofs with images in them. So it's important to let you know what you can assume is true and what you can't assume is true. So you can assume that definitions, axioms, postulates, and properties are true. If anything is given, you can assume that is true as well. So assume that it's a given property for that specific problem. So in the drawings, the things you can assume are true are collinear points. If 3 points look like they're on the same line, then they're on the same line. You can assume the betweenness of points. If I show A, then B, then C, B is definitely between A and C. You can assume that that the points are coplanar unless we say something else. So most of the points are going to be on the same plane. You can assume that straight angles are straight 180-degree angles and straight lines are straight lines. You can assume adjacent angles, angles that share a ray, are adjacent, that they are touching. You can also assume linear pairs of angles. So that's where you have a straight line and an angle coming this way. You can assume that both angles make a straight angle. And you can assume vertical angles. So if you have two lines intersecting, these two are vertical angles, and we'll talk a little bit more about those. Now, here's what you cannot assume to be true. You cannot assume the measures of segments. You can't, if one looks like it's twice the other, that doesn't mean it is twice the other. Only if you see something like congruence marks that help you measure it out, that's when you can assume lengths. But otherwise, unless it's marked, you can't assume it. Same thing for measures of angles. A lot of people want to assume that something that looks like a 90-degree angle is a 90-degree angle. You can't. You can't assume two segments are congruent just because they look like they're the same size. Only if they have congruent marks on them can you assume that they're the same size. You can't assume angles are congruent unless they have the congruent marks. And you cannot assume right 90-degree angles unless there's a square there or it says 90 degrees in that angle. So some of the properties you're going to find useful for our proofs are the multiplication and division properties of equality. The first one is the addition property of equality, which says, well, if I say A equals B, then I decide to add C to both sides. Will both sides still be the same? Yeah, if, for example, if we used a scale, and I stood on the scale and then I put some weights on the other side of the scale. If you gave me a geometry book here, and then you put a geometry book on the other side, the scale should still balance, right? It should still be equal. So if you have an equation and you add the same thing to both sides are still equal. The subtraction property of equality works the same way. If you subtract something from both sides of an equation, both sides are still equal. They're still the same. For multiplication and division properties, well, we have the multiplication property of equality. So if I have an equation that I start with, and I multiply both sides by the same number, then both sides are still the same. So if I double one side and double the other side, that's still a good equation. They're both sides are still equal. If I double, then triple, that's a different thing altogether. Same thing for division. If I divide both sides by the same number, the equation is still valid. So multiplying or dividing both sides of an equation by the same thing will still keep both sides equal. The reflexive property of equality says something equals itself. A is A. A will never not be equal to A. So you can always say something equals itself. The symmetric property of equality says if I write A equals B, then I'm allowed to write B equals A. And so you can switch two sides of an equation if it makes it easier to work out. The transitive property of equality says if A equals B and B equals C, then you can skip the middleman. You can skip straight from A to C and then just say A equals C. Substitution looks like it works a lot like a transitive property, and we actually use the substitution property a lot in proof. We say if A equals B, then B can be substituted for A in any expression. So for further reflection, what can you assume is true in diagrams? What does it mean for two things to be equal?